Hello and welcome to my video contribution for the German Probability and Statistic Days 2021 happening virtually in Mannheim. My name is Tobias Fissler and I'm an assistant professor at the Vienna University for Economics and Business. The title of my contribution is Backtesting CoVaR forecasts using multi-objective elicitability. It is based on a joint preprint with Yannick Hogar, and you can find the link to this preprint on arXiv here on the title page. Okay, what is CoVaR? It is a special instance of systemic risk measures. What do we need to care about when it comes to measuring the risk of a certain financial system? Well, it is well known that univariate attempts of measuring risk are inadequate. Why is this the case? Well, usually financial institutions exhibit strong tail dependence. That means if one institution is in distress, the other ones are much more prone to being in distress as well. And here we can see an example of the DAX and the S&P 500 between 2000 and 2020, daily log returns, negated daily log returns, and you can see that volatility clusters basically happen simultaneously, and on the right you can see a scatter plot of the log returns, and you can also see this strong tail dependence. So introducing some notation, let y be the losses of main interest and x be a reference position, for example the aggregate of the market. Then Adrian and Brunnemeyer defined the CoVaR, which measures the risk of y given that x is in distress. They used the stress event that x equals the value at risk at level beta. We, on the other hand, define the stress event as x exceeding its beta value at risk, and then CoVaR of y given x at level alpha given beta is simply the alpha quantile of y given that x exceeds its beta quantile. Okay, so in the paper we also consider other systemic risk measures, but in the talk we will solely focus on CoVaR. Okay, how can we backtest systemic risk measures? Backtesting is about validation of forecasts, but we won't talk about that here for the sake of time. And the second is about comparison. What do we mean with comparison? So suppose you have two different risk measure estimates, maybe coming from two different models, and you have observations. How can you judge which one is more accurate for the risk measure? Well, you need the notion of elicitability. We say that a risk measure is elicitable if there is a strictly consistent scoring function S being a function of the forecast and the observation Y, and being real valued such that its expectation with respect to Y is minimized if and only if we plug in the correctly specified risk measure estimate. And for example, value at risk is elicitable with the asymmetric piecewise loss or the pinball loss. Expected shortfall fails to be elicitable. Now, what are the problems when it comes to backtesting CoVaR? The problem is that CoVaR does not possess convex level sets, and this is a necessary condition for elicitability. So we have a problem when it comes to backtesting CoVaR forecasts. But what can we do? Well, the nice thing is that we have conditional elicitability. We say that a risk measure rho 2 is conditionally elicitable with rho 1 if rho 1 is itself elicitable and rho 2 is conditionally elicitable for every pre-image of rho 1, right? So this here is a pre-image, this FV, and this needs to hold. So for example, variance is conditionally elicitable with the expectation, and expected shortfall is conditionally elicitable with value at risk. Here we have the same. CoVaR is conditionally elicitable with var of x. And here is a strictly consistent scoring function for these pre-images. Okay, now how can we use that? The problem is, unlike mean and variance or value at risk and expected shortfall, the pair still is not jointly elicitable with the usual scoring function. To remedy that, we introduce multi-objective elicitability. So usually we work with univariate scores. Why? Because of tradition and because there is a canonical order on R. So we know which one is larger or smaller. We introduce multi-objective scores, and here I will only talk about a certain notion, namely about bivariate scores, which are equipped with a lexicographic order. So just to recall it, the lexicographic order first looks only at the first component, and only if there is equality in the first component, it considers the second component. Okay, and one can define multi-objective elicitability with respect to the lexicographic order, basically just in a similar way as the usual elicitability. You just replace the inequality with an inequality with respect to this total order. And it turns out that conditional elicitability implies multi-objective elicitability with respect to the lexicographic order. So that's a novel finding. How can we exploit that? Well, we can exploit the conditional elicitability and come up with strictly F-consistent multi-objective scores for VAR and CoVaR. They are of this form, and there is even a richer class of such strictly consistent scoring functions. Okay, so that means we're in a position where we can really compare different risk measure forecasts for CoVaR and VAR. So how can we use them in a Diebold-Mariano setting? Okay, so let's suppose we have two bivariate risk measure forecasts for VAR and CoVaR, and we have bivariate observations of xt and yt. Then we consider the score differences. They are bivariate score differences, and under certain mixing conditions and so on, and stationarity conditions, we have a bivariate central limit theorem. And we can use this bivariate central limit theorem to introduce level new tests. One is the null hypothesis of equal predictive performance. And this is pretty straightforward to test. Here is the non-rejection region. It is the classical ellipse we know from Wald tests. And yes, this can be readily applied. One can also transform the test statistic to a chi-square distribution, and everything goes pretty well. For one-sided tests, one needs to be a bit more careful. One needs to look at what null hypothesis to test. And we elaborate on that a little bit in the paper and argue for the following, say, 1.5-sided test statistic, that we have comparable CoVaR forecasts, comparable VAR forecasts, but that one forecast is superior in the CoVaR component, because this is the component of interest for us. Okay, so in mathematical terms, the null hypothesis looks like that. And the non-rejection region has this, well, half ellipse shape plus a column around, like a stripe around the y-axis. And we are able to control the size and to derive asymptotic level new tests. So that's possible, and all that is novel. And this gives rise to a so-called traffic light approach in a regulatory setting. So yeah, what's the idea? Well, rejecting the null hypothesis, this 1.5-sided null hypothesis, can have different reasons, and we give an interpretation. So suppose the R tildes are a bank's internal model, and we have R1 and R2 from the regulator's standard approach. And then the question is, okay, are the bank's internal forecasts really superior, but only the CoVaR component? And we generalize the three-zone traffic light approach by the Bank for International Settlement. What does it look like? So we have a traffic light with 1, 2, 3, 4, and actually 5 colors. In the yellow region, both components are comparable. In the green, the CoVaR is superior and the VAR is comparable. In the orange, CoVaR is inferior and VAR comparable. In the red, VAR is inferior, and in the gray, VAR is superior. And yes, here are some more details. And just to round it up, here is an empirical example for the DAX and the S&P 500. We fitted two models, a reference model with Gauge 1-1 marginals and a Gaussian copula, and then a more fancy internal model, which is kind of the state of the art, and fitted that, estimated it, and here is basically the result. So we were able to reject the 1.5-sided null hypothesis and really say that we have superior CoVaR forecasts. Okay, so this is a summary, and thank you very much for your attention.